just reverse the time. So last data point actually comes first into the filter, and do it both ways through the filter, and it removes the phase shift. So it's 0 phase shift. But of course, it's not real-time operation, but it's a dirty trick that scientists use. Sometimes even engineers do it. All right. Group delay. Group delay is the phase derivative of, the frequency derivative of the phase shift. So basically, for linear phase response system, group delay gives the constant, which is same as the time delay. It's the constant time delay. It's directly that one. On zero phase response, it has 0 time delay, meaning that group delay is 0. Non-linear phase response system will skew the signal, but anyways, then you would have a say varying group delay, and group delay gives basically the time delay of the signal on different frequencies. I think I have some pictures of it. Okay, yeah. Okay, I have a kind of nice test signal there, just a kind of uniform signal and zeros on both sides. For linear phase response, you have exactly the same edges. So the linear phase response system basically means that if you have rising edge or falling edge, but otherwise the shape is the same, then it does not change the shape. It stays like that. Nonlinear phase response, this is, I think it was second degree system. Quite familiar what you get from any analog system. So there's a little bit of overshoot, but then actually it comes as an undershoot for the falling edge. On linear phase response, you have equal amount of undershoot and overshoot for the both rising and falling edge. Zero phase response, meaning that actually you have the filtering capabilities here exactly the same as on the say nonlinear phases, but well, the time shift is 0, and that's why you cannot do it in real time. You cannot calculate these values before you are actually having any data. So, but post-processing, yeah, why not? Good. Spectrum analysis. So now we had the impulse response, step response, sinusoid, or any other response. We had transfer function. We have zeros and poles, how to relate to the frequency response. How about now one more step and going back to the signal and taking a look at the how to analyze the signals. That's simply done by Fourier transformation. The power spectrum definition is right there. So you take the signal xt and calculate the Fourier transform, and basically that's the second norm. You multiply it with the complex conjugate of the same Fourier transformation. In MATLAB, that's how you do it. Okay, with sample data you use discrete Fourier transform. Well, you call the function. You don't have to use it otherwise. You don't have to make the hammer in order to use it, you know. The practically the fast Fourier transformation is the way to go. However, there is a caveat. The fast Fourier transformation works only if the number of sample is 2 to the power of something constant, a integer. So 2024 is okay, 4096 is okay, 9192 is okay, but it doesn't. 193 is not okay. Okay. Yeah. Then there are some other artifacts. Spectrum analysis. This is a real Fourier transformation what I did for sample data like that with 1000 data samples. On analog world, you can wait for a while until this actually settles into one single peak. But in digital world, you always have this envelope that comes from the fact that, from the physical fact that these signals actually obey mathematics. When you take the Fourier transform of this data, it's not actually just Fourier transform of the sinusoid, but also the window function multiplied by window function. So if you basically some mathematicians has found that okay, if you have a multiplication of this one, it's the same as you do convolution in frequency space, meaning that actually you get peak from the sinusoid, and this envelope actually comes from the Fourier transform of the window function, which you always have since you have limited number of points. So it's like looking from the window. There will be some exercises for that one, but I will just show some nice pictures. Okay, single spectrum is kind of nice, but on the other hand, if the signal was such that you can define it only by one single spectrum sample, it will be really boring. How about if we have a varying frequency on the signal, for example, as in real life. This is another test sequence. It's a chirp signal, meaning that the frequency is changing linearly by time. So basically here we have some, zero frequency on the beginning, and then it starts, going higher and higher frequency. For that one, to analyze that one, a single the Fourier transform would give you just flat response, flat spectrum. But if you calculate the spectrogram, it actually shows you how the spectrum is varying by time. So there's time on the horizontal axis, frequency on the vertical axis, and then this color-coded picture of how the frequency is varying, how the power is distributed over time and frequency. Okay, soon we will have a break, but anyhow, let me explain that a little bit, since it helps probably understanding the spectrogram better. So spectrogram time versus frequency. Uh, and then can you imagine what that could be? That's actually the ambulance. Tee-ta, tee-ta, tee-ta. And then yeah. So it's actually the spectrogram is used as a image representation of a sound. The first people to use it were actually, well, non-military persons to use it were the ornithologists, describing how different birds actually are singing. So they could have, or, and just drawing that kind of images on the on the margin of a bird manual. Okay. Then there was the Second World War, and there were also another applications for the this one. And now there are plenty of other applications. Submarines. How to find out if a submarine is actually ours or the enemy. You listen, signatures, and then drop bombs and say, oops, oh, it was ours. Okay, but let's have a break and then come back at 3:15.